Okay, so let's get started. Okay, so today we are going to talk about some other functionalities that you can do inside database, actually go beyond what you are doing, like what we are learning in the last couple months about the relational queries. We are going to talk about something that goes beyond relational queries. So this is what we already know, right? So what is a database instance, right? So it's a whole bunch of relations, and each relation contains a set of tuples, right? So, and we talk about how to manipulate and how to query the data given a database instance, right? So we know how to write a query. What is a query? So far a query is a function that take as input a database instance and output a new relation. So this might sound like a very natural way to define it, but this doesn't come from nowhere. This is just a consequence about how we think about our data and how should we model it. That's very important because once you understand where this notion of query comes from, you can actually try to change some of your kind of assumptions, some of your view on what data is, and then you can actually enable a whole bunch of different functionalities. So where does this come from? Right, so far when we are thinking about database, we actually take a pretty logical view of that, right? So we talk about the close connection between a SQL query and relational algebra and relational calculus, which underneath the cover is essentially try to find a finite model for a first order logic formula. But when we think about the database, we are thinking about it as an instance that form an interpretation of some logic system, right? So that's a very abstract way to say. But if you look at the professor table, our current view is this gives us a logical predicate. And in this interpretation, only 3 tuples is going to evaluate to true, and all the other tuples are going to be evaluated to false. And under that interpretation, you give me a query, which is a logical formula, and then I try to answer it. So that is essentially our current view of database. Because of that, we design our query languages. The declarative way is essentially you write that logical formula for me. And then we talk about relational algebra and their equivalence. And then we design something that's easier for human to use, and that is SQL, right? So that is the connection between your view on data and your way of querying that piece of data. In this lecture, we are going to kind of take a different view. We are going to take a more statistical view of database. And then you can see once you take that view, the notion of query is start to change. And that can actually enable a whole bunch of other type of functionalities that goes beyond relational query. So in this lecture, we are going to think about the database instance, not as the interpretation of some logic system, but more as a set of samples that you see from the history. And then our goal is really taking that samples from the history and learn something about the future. It may not come from the history. For example, if you are doing census, right? So you are actually taking a whole bunch of samples of your population. What can we learn from that? If you take this view, the notion of query actually goes beyond a logical formula. We can actually define different ways that you can extract insight from your data. And that is something we are going to talk about today. And that brings us to a whole bunch of fancy topics, for example, data mining, for example, how to do machine learning inside database, which is a very important skill to have nowadays. Right? It's a huge area on its own. And in this lecture, we will just scratch the surface. We will not go too deep into each of these topics because they can be their own like whole course, right? But we really want to make sure you guys understand in a modern database system, there are functionalities that you're able to do beyond just answering relational queries. So the content of this lecture will not be an exam, right? So we can have some fun, right? Just relax, and then we can walk through all those kind of fancy functionalities. But we are not learning for the exam, right? We are learning for the knowledge. right? So what do we want to achieve in this lecture? So first thing I really want you guys to understand, there are operations that you can do beyond relational query. I do not want you guys to take a 1970 view on what data is and what database is. There are a whole bunch of, it's not only a system to answer SQL queries. It is a system that can actually process data, and it can support so many functionalities, goes beyond a simple SQL query. And second, I want you to know that for many of these operations, data mining, machine learning, you can do them very naturally and easily inside the database management system. And when you go to the real world, right, you will see some applications, it actually makes sense for you to bring the data out of your database or bring your data out of the file system and run that in a separate data mining or machine learning system. That happens, okay? But for many of the operations, you are able to bring the computation as close to data as possible without really copy the data out of the data ecosystem. So that's another thing I really want you guys to know. And third thing is, if you think about database management system, I do not want you to think about it as just a storage of data and an execution engine of a scan or join operator. It's not what a database is today. Database, it can also help you to get insight out of your data. Another thing I really want you to know is, if you need all these functionalities in the future in real world, right? When you find a job, you find out that application, you need some analytic functionality. I hope to remember where to find them and where to start in learning them. Okay, so this is just a pointer for you when you go to the real world. We don't need data mining, they need machine learning inside database. Remember this lecture. Remember that is something that you are able to do inside database. Okay, so this is a huge topic, and there are many slides that we have today. They are actually adapted from a Stanford course called Mining Massive Data. You can actually find the material here. There's actually a lot of other topics, right? So in the in this course, and we will not we will not have time to cover all of them. If you are interested in those analytics type of thing, right? So this is a very good pointer to have. Okay, so in this lecture, we are going to talk about 3 advanced analytics functionalities you can do inside the database system. The first one is related to data mining, right? So when you talk to other people about data mining, right? So often, well, from the academic point of view, often people mean associated rule mining, okay, precisely. And then we are going to talk about 2 machine learning functionalities. One is clustering, another is classification. So let's start from data mining. What is the motivation here? So motivation here is actually very simple. So you have, for example, you are running a supermarket, right? So you know some items are often bought together, right? So for example, when people buy bread, and people also buy milk, right? So there's all those strong associations between different items. You could store them, for example, in a relation that looks like this. You have 5 different transactions, maybe corresponding to different customers in your supermarket. And for every single transaction, you know the set of items that that customer bought in that during that transaction. For example, the first customer, right? She bought bread, Coke, and milk, right? Second one, the second transaction is beer and bread, so on and so forth. First one, as we can see, this schema is not in first normal form, right? So if you think about the database design theory, this is not something in first normal form because it doesn't have atomic values, right? You can actually decompose the items column into a whole bunch of smaller columns, like into a whole bunch of smaller kind of items, right? So it's not in first normal form, but we don't really care here. So one thing that you really want to understand is, okay, so I have all those co-occurrence of items. I want to see, for example, what are the item sites that frequently appear together. And here we can actually define the notion of support. Essentially, if you give me an item site I, for example, beer and bread, this is one subset of items, right? So I want to count how many baskets or transactions contains all the items in I. In this example, right, so you can see if I want to compute the support for beer and bread, right? So the first transaction doesn't have it, the second transaction have it, and then the first transaction have it, right? So the support of this item set is 2. And often people kind of express it as a fraction of the total number of baskets, right? So here essentially the support is, and it could be 2 or it could be like 2 out of 5, right? You could normalize it to make sure it's more easier to understand. And the one problem people find themselves like often interested in is given a support threshold S, can we find all the item side for which at least S basket like contain that item set? So essentially, if the support of certain item set is larger than S, we call it the frequent item set. And then the problem that people often cares about is I want to find all the frequent item sets given a support threshold. So here's one example, right? So assuming we have 5 different items, and assuming our support threshold equal to 3, and then assuming my database contains all these kind of 8 transactions. The first one has milk, has Coke, has beer, right? So on and so forth. So what is the frequent item set here, right? So it's actually very easy to see. So there are item set only contains essentially 1 item. For example, if you think about milk, it appears in B1, B2, B3, right? B5, B6, right? So the support of this, of the milk item set, the first one, equals to 5. It's larger than 3, so it's a frequent item set, right? In this context. And then you can look at the combination of those. For example, if you look at milk and the beer, right? So it appears in B1, it appears in B3, appears in B5, appears in B6, right? So the support of the item set M and B is 4, larger than 3, so it's a frequent item set. So in fact, all of these item sets are frequent in the sense that they have a support larger than 3, which is the threshold that you define, right? So in your database. So here's just one example of this. So why do people cares about support, right? Why do people cares about 2 things appear frequently together? It's because once you have support, you can define something called association rule. It is a whole bunch of if-then rules about the content of your transactions. So here we write something like this. So left-hand side is one item side, and the right-hand side is another item side. This means that if you have a transaction containing all the items on the left-hand side, then it is likely to also contain items on the right-hand side. If you are kind of building a supermarket, right, you can think about this as very useful for doing recommendation, right? If someone already bought milk and bread, maybe we should recommend peanut butter and jelly, whatever, right? So, and then once you have all those association rules, you can enable the extraction of insight from data and to enable applications such as recommendation, right? Assuming you are building Netflix, you are building the next Amazon, right? When you have observation on the behavior of the user, right? You could actually extract all those association rules from the data. So in practice, there are so many of these rules, right? So we want to find those significant and interesting ones. And then we to define what do we mean by significant and interesting, right? One way to define it is to define the confidence of this association rule, which is essentially the probability that a transaction contains the right-hand side given the left-hand side. And you can do that precisely by using the notion of support. Essentially, we can define the confidence of association rule from I to J as the fraction between 2 numbers. First one is a support of I union J. That is, I want to see how many transactions I have in my database contains all the items in I and J. and I divide that by the number of transactions in my database that contains items in I. Essentially, condition on the transaction contains all the items in I. What is the probability I'm going to also see J there, assuming all the transactions follow some uniform distribution, okay? So that is the confidence of this association rule. But what's interesting here is confidence often might not be the thing that you want, because not all the high confidence rules are interesting. So we can actually think about one example. Assume you have a rule from X, some item set to milk, okay? So and assume that milk is the item that people just going to buy no matter what, right? In the extreme case, all the transaction will have milk. In that case, right? So this rule is going to become really a high confident one, no matter what you put on the left-hand side, right? Because people are going to buy milk. I don't care what you have in X, people are going to buy milk, right? So that means the notion of confidence might not be enough to describe whether a rule is interesting or not, right? So another notion of something being interesting is we can define what people call the interest of association rule. And that is actually the change of probability given the left-hand side. So essentially, the interest of a rule from I to J is defined as follows. It is the confidence of this rule minus the probability that J appears in some transactions. Okay, so you can think about this, the right-hand side, as the support of J, right? How many transactions you have in the database contains J over the total number of transactions, okay? And then this thing, confidence, is condition that I know the left-hand side, like condition on the fact that I know this transaction contains all the items in I, what is the probability I'm going to find J, right? You can think about this as your boost of confidence or decrease of confidence, right? By knowing that you have I in your transaction. So here's just one example, right? Assuming we have this 6 different items, and then we have 8 transactions, right? So let's look at one association rule from MB to C. So here, if you want to calculate the confidence, how to do that, right? You calculate the support of M, B, and C. You count how many transactions you have in your database contains M, B, and C. In this case, you have B1, have that, B6, have that. And then you count how many transactions you have only contains the left-hand side. Right? So in this case, you have B1, you have B5, you have B3, you have B6. So the confidence of this rule is 2 over 4, like 0.5. And then we can compute the interest of this rule. It is the confidence minus the probability that C, the right-hand side, appear in your database. In this case, you first compute the support of C, which is you have B1, you have B7, you have B4, you have B6, or B8, right? So it's like 5 over 8, right? So that's a probability you are going to see C in your transaction. And you compute the difference between that and your confidence, you get the interest of this rule is 1 over 8, right? So, and you can see after you calculate the interest, this rule is actually not that interesting, right? Because it doesn't really, because knowing M and B, the left-hand side, is in your transaction, is only going to alter my confidence or like alter my belief about whether C is going to be there or not by 1 over 8, right? So that's a very small thing. So you can see the kind of the relationship between support, between confidence, and between interest, right? So and you can actually get a very intuitive feeling about why people cares about this type of things, because they will kind of extract a whole bunch of rules from your data. So the problem is as follows that we want to understand. That is, let's try to find all the association rules with support higher than S and with confidence higher than C. Okay. So later, if you want to kind of like find those with high interest, right? So you can actually apply a very similar algorithm. So let's assume this is our problem. As you can see, it's not going to be that trivial, because how to find that efficiently over billions of transactions is actually a very, very hard task that people have been working on for decades. So the hard part is really try to find frequent item sets. Okay, given a support threshold S, how can we find all the item sets with support higher than that? So that is actually the hard technical problem. So how can we do that? So people have been studying this for decades, and here's actually one very simple algorithm that we are going to talk about. So, and the goal is really try to find like all the association rules with a high support and also high confidence. So the first step is to find all frequent item sites. Okay, so we will talk about how to do that later. And then once you get all those frequent item sites, you kind of generate rules out of those. So for each of the I, you already know is high support after step 1. And then you can look at every single subset A of I, and you can actually generate a rule from A to the rest of items. For example, if you have one frequent item set that is, for example, beer and milk and Coke, right? And you can look at, oh, let's look at one subset A equals to milk, right? Then I generate a rule from milk to the other 2 attributes. And you do that for every single subset of I. Since A is frequent, you know A is also frequent because that's a subset, right? And then you can actually do a whole bunch of filter like process. For example, you can do a single pass and compute the confidence of this rule, right? So for example, like if A, like in your case, right, left-hand side is AB to CD, right? You can just have a lookup table and compute the support, right? And then you can get the confidence. You do one pass of filtering on the confidence. Or in some other algorithms, right? So you can actually generate bigger rules from the small one, right? So the observation is, if you know that A, B, C to D is below certain confidence, then you automatically know that AB to CD will also be below that confidence, right? So once you know some rule is actually below confidence, you can ignore a whole bunch of other rules, right? You can actually grow the rules from a small one to a bigger one, right? So depending on different algorithms, you are going to have different ways of filtering all the rules like below a certain confidence. And then after step number 2, right, you filter all those rules with low confidence, right? So then you can output whatever rules you have that is above the confidence threshold. So as you can see here, right, so a fundamental step in doing this is really try to find frequent item sets. That is, you give me a database of transactions. I want to find a subset of items that appear frequently, more than, for example, S times in my database. And doing that is actually very hard. But let's look at one concrete example first, right? So assuming, again, like this 8 transactions, and assuming our support threshold S equal to 3, right? We only care about rules whose support is larger than 3, and our confidence threshold is 0.75. Right? In this case, let's try to find all the frequent item sets, right? So like for this example, right? So it's going to like look like this, right? So, and then we can generate rules, right? You can actually take, for example, one item set, B and M, frequent item set, then you generate a rule, for example, B to M, you take B to C, you have B to C, right? So you can generate a whole bunch of those. And for each one of those, you can calculate their confidence, right? You can filter out all the rules with low confidence, then you get what you want. So as you can see, the core part is really try to find frequent item set. That is step number 1, because once you have step number 1, step number 2 will be relatively simple to do. So how can we find frequent item sets? That's actually very, very interesting. So the structure of the problem is going to look like a lattice, okay? So assuming you have 5 items in your database, you can have an item set that's empty, contains nothing. And you can have one item set contains pretty much everything, A, B, C, D, okay? And then you have all those subsets in between. So as we are going to see, it's going to form a lattice, right? You can actually take this structure and try to do a whole bunch of pruning over this. We are going to see that later. Okay? So, but one thing that we need to understand is, assuming you have D number of items in your database, how many possible item sets, how many possible nodes we are going to have in this lattice. So we are going to have 2 to the D possible item sets, right? For example, like you have empty set, you have the set with everything else, right? So essentially you can encode the whole thing by having a single bit associated with each item. So you have 2 to the D number of possible item sets, right? So clearly, if D is very small, right? In principle, I can just go over all the possible subsets, and for each of them, I calculate the support, then I'm done. But as you can see, when D grows, right? When you talk about you are building a supermarket, there are millions of items where D equals to millions and number of transactions equals to billions. It's not really clear how to do this in a very efficient way. And that is something that we are going to talk about. So here's a very naive algorithm, which is going to give you some baseline to work with, and then we can take it and improve it. So it's brute force. Each item set is a candidate, right? So I can store all the candidates. Okay. In this case, if I have my number of items equals to D, I could just store all of those in a table, right? Which is going to have 2 to the D number of rows. Okay. And for each of these item set, I just go through my whole transaction table and I just calculate the support, and then I do one pass of filtering them done. Okay, so this is a naive algorithm that does not really scale. We don't have a large database, but anyway, it gives you a baseline. So what is the time complexity, right? So it's going to be linear to number of transactions, going to be linear to the largest transaction, essentially like you think about that as number of columns, right? And then it's going to be linear to the number of candidates you have. In this case, going to be exponential to the number of items you have in your database. So as you can see, it's very expensive. So we have to do better. So let's talk about one really classic algorithm here. So at some point, this used to be the highest cited data mining paper in history. I don't know whether it's still true or not, but when I was an undergraduate student, it used to be the most highly cited data mining paper in the world, right? So it's actually a paper that proposed a very simple way of calculating a frequent item set. So what is the principle? What is the observation behind this algorithm? So the observation is actually very simple. If one item set is frequent, then all of its subsets must also be frequent, right? For example, if the item set milk and beer appeared like twice in your database, then if you take every single element or subset of that, it must appear more than twice, right? Or equal to 2, right? So if an item set is frequent, then its subset must also be frequent. And also the other way around, right? If an item set is not frequent, then all of its superset cannot be frequent, right? So this algorithm is actually based on this very, very simple observation. But you can actually use these 2 observations to prune that lattice. Okay. So essentially, the intuition behind it is if you take this lattice, right, every single node is one possible item set. If I can find one item set that's frequent in the lattice, for example, assuming CDE is frequent, given my support threshold, then all of this part of the lattice is also going to be frequent because all of them are just a subset of this frequent item set. So I do not need to enumerate all of them. I can just like find CDE and ignore this whole region because I know they will be frequent. On the other hand, if I know some item sets are not frequent, for example, if I know AB is not frequent, right? So then I do not need to care about this region anymore because all the superset of AB will also not be frequent. Okay, so this algorithm actually based on these two very simple observations to prune this lattice. Okay, so here's the algorithm. You maintain essentially two data structures. One that is something we call CK, another we call LK. So the CK is a candidate item set of size K. So they are all the item sets that we believe has a chance to be frequent, and they have size K. Okay, and then LK is a frequent item set of size K. Essentially, we are going to take CK, and we are going to check the support for each of them, and then generate LK. We maintain this two data structure for different K. Okay, so at the very beginning, you have K equal to 1, and we set C1, that is all the candidates of size 1 equals to all the items. Okay, if you have D items, C1 going to have D items. So, and then what I'm going to do is from 1 to K minus 1, you generate an item set with size K. Okay, you always grow the size. Essentially, you keep checking whether CK is empty or not. If CK is already empty, it means that you do not really have any frequent items of size K, right? So you don't need to care about K plus 1 anymore because all the superset is going to be less frequent, right? So if this set is also like not frequent, so you check whether CK is empty or not. If CK is not empty, you scan the database to find which item set in CK are frequent and put them into LK. And then you use LK, the frequent item set of size K, to generate a collection of candidates of size K plus 1 and put them into CK plus 1. Okay, so this is a very simple structure of this algorithm. So here's one illustration of this, right? So at the very beginning, you have your C1, right? So this is actually like all the kind of item sets of size 1, right? So and for each of those, you can see, oh, this is how many times it appears in my database. So what you are going to do is you are going to take this, and generate essentially a candidate set of size 2. And as you can see, right, so here I have 6 of these items. If you consider all the pairs, right, so I should have 30, like 30, right, so of those pairs, right? So, but however, if you think about this kind of candidate sets, not all of them should be there, right? For example, if my minimal support is 3, if you take Coke, which appear twice, if any set contains Coke, it must not, it cannot appear more than twice because the, like item Coke only appear twice in your database. As long as you have some item set contains Coke, the support of that set must be equal or smaller than 2, right? So that is why in the candidate table, right, you will not have Coke, you will not have X, right? You have everything else, right? So that's one part of pruning, right? You do not need to generate all the combinations for your candidate set. And then for each item in the candidate set, you can calculate a support. For example, here you have bread and beer, right? The count is 2, right? It's smaller than 3, right? So you can actually get rid of this. And then you keep doing this. You keep growing the size. As you can see, you can actually support pretty aggressive pruning, right? If you just based on that 2 very simple observations. So now let's make that algorithm a little bit more concrete. Talk about some way to generate candidate sets. So essentially, what do we want to do? So here, when you generate a candidate, one principle is that an item size of size K plus 1 is a candidate to be frequent only if all of its subsets of size K are known to be frequent, right? If any of the item set of size K is not frequent, then that item set K plus 1 is also not frequent because by definition, its support cannot be higher than any of its subsets, right? So essentially when we generate CK plus 1, we are going to take LK which is all the candidate sites that we know to be frequent of size k, and then find another larger item set of k plus 1, for which all of its subsets are in LK. So that is actually the game that we are going to play. So how can we do that? There's actually a very simple way to do it. So, and that's actually kind of beautiful. So assuming all the items in an item set are ordered, okay? So if you are talking about every single item is encoded as an integer, right? So you can just order them like by comparing all those integers. If you have string like milk and whatever, right? You define order, okay? So assuming all the items have order between them, so then what you are going to do is that you can actually store them. You can put them like inside the table, where like this is actually kind of essentially like L3, right? So this is actually all the item size with size equals to 3, and then you can actually order them 1, 2, 3, 1, 2, 5, so on and so forth. This is actually 3 kind of item size. Okay, so the reason we want to order them is we do not want all those have like duplicated information inside it, right? So you put them in relation of k columns, right? Each row in the relation corresponding to one frequent item set of size k, right? And then whenever you store them, you always maintain the order. And then what we are going to do is, if I want to create an item set of size k plus 1 out of this, I can actually join this relation with itself, and to generate one that's generate a new tuple that share all the k minus 1 attributes, but are different in the case attribute. For example, if you look at the two tuple 1, 2, 3 is frequent, 1, 2, 5 is frequent, you can actually take them and generate 1, 2, 3, 5. Okay, so by doing this, you can actually generate a whole bunch of candidates. So this might sound a little bit counterintuitive, but think about this example, right? So why do we kind of enforce the first 2 columns to be the same, right? So what if they are not the same, right? So are we actually missing some candidates? Actually, no, right? So for example, if you have 1, 1, 2, 4, 5, right? If they do not share all the previous attributes, right? So in this example, it actually means that, for example, 1, 2, 4 is actually not frequent, right? Because otherwise you are going to generate this tuple from 1 to 4 and 1 to 5. The only reason you are relying on 1 to 5 and 1, 4, 5 to generate this example is because 1 to 4 is not there. Because 1 to 4 is not there, that is the subset of this larger item set. It actually means that this one will not be frequent for sure, because you constructively find one subset here, 1 to 4, that is not frequent at all, right? So that is why this is actually kind of correct. So this actually gives you a way to run this algorithm by writing a very, very simple SQL query. So assuming you already have LK, right? You can actually do a self-join between LK, and then you actually match all the first k minus 1 attributes, and then you generate kind of item set of size k plus 1. Right? If you do this, take this example, right? If you run this SQL query, you are going to get a larger candidate set. And then you can actually take that candidate set, you run the tuple by tuple, right? And for each of them, you calculate the support, you do one part of filtering, you get your LK. Okay, so it's a very, very simple algorithm. So this is actually one of the first algorithms for finding all the frequent item sets. And after that, people have spent actually almost 2 decades. I don't even know whether 2 decades or 3 decades, a long time, to develop a whole bunch of more efficient algorithms to further improve this. So it's a very large area. So inside database, right? So like PostgreSQL, that is something that you can actually do. So this is just one example about how to approach this. Assuming you have one application, you need to find all the item sets with high support. So what can you do instead of kind of implementing that by yourself, right? So once you can do is, it's actually here. So there's one package called Madlib. Actually, if you are using PostgreSQL, right? So this is one of the most popular library to support a whole bunch of analytics functionality. So once you can do is kind of create a table, for example, test data in this example, and then you put the transaction ID and the product here, right? So this one will give you some schema in first normal form, right? So you can have, for example, the first transaction has beer, the second transaction has diapers, the third transaction has chips, so on and so forth. You put them in a relation where the first attribute is transaction ID and second attribute is product. And then you can just run something like this. It's very similar to a SQL query, but as you can see, here is a special function that you need to use, right? So essentially this one will take as input your relation here, all the information are here, and you'll tell it, okay, so this is my transaction ID, this is my my product name, right? So this is the to name of the column, right? So this relation name. You tell it, okay, I want to find all the association rules with, for example, support larger than 0.25 and have confidence higher than 0.5, right? So if you run this, the database is going to automatically create a new relation for you. And then if you query it, it's going to contain information look like this. So as you can see, this column is the left-hand side of the rule. This thing is the right-hand side of the rule, right? So if you look at this row, let's actually say, okay, I have a rule in your database from diaper to beer, right? So, and the support look like this. So this is my confidence, right? So you can have some other property of the rule, right? So we don't care about in this lecture, right? So you can actually get all this table automatically, right? By just calling this very simple query over your data, right? So this definitely goes beyond relational queries, right? You cannot have a relational algebra expression for this, right? But this is something that you are able to do inside database. And people have spent decades to really optimize it, in the sense that if you give me a database with billions of transactions and a couple millions of items, right? So we do have a very efficient algorithm for to do it, right? In some, when you are building your application, we will need this functionality, right? Maybe it's not the best idea to implement that all by yourself because I'm sure it's going to be slow, right? I mean, you are smart, you can always optimize it, but inside a modern database, this is something you can do almost automatically. So, and you can actually introduce a whole bunch of constraints, right? For example, you can actually change the parameter, like in your query, to say, I only cares about, for example, item size with maximal size equals to 2. I don't want item size too large, right? If you do this, you are going to have a smaller table, right? You can only see, there's only output all those rules whose maximal size equals to 2, right? You can introduce a whole bunch of constraints. You can say, I want a whole bunch of rules where the right-hand side only contains a single item, and I don't care about how many items you have on the left-hand side, right? If you do this, you are going to get essentially what you're asking for, right? So, and for this, right? So once you have this, you can actually how to read it, or you can take one row to say, so most of the transaction with chip will also have beer in it, right? So the conditional probability of beer condition on chips is actually pretty large, right? And you can use that to get some insight from your data. So this is the first half of this lecture, and we talk about associated rule mining and show some example about how to do that in PostgreSQL actually, right? So let's take a break. In 15 minutes, when we get back, we are going to talk about the clustering and the classification. Okay, so if you have any questions, I'll be here to answer them. Yeah, thank you. Okay, so let's get started. Yeah, in the first half of the lecture, we talk about associated rule mania, right? So that is how to kind of find all the association rules with high confidence and high support, right? So once you have those, you can think about you have essentially a very good recommendation engine. You know the correlation, right? So if you find some user kind of buying something, right? And from some association rule, you can say, yeah, maybe I should recommend some other things for that user, right? So the benefit of doing that inside database is people have been optimizing it for decades, right? When you have a very large database, right? So you can actually put them into a modern distributed database system that's going to run that on a whole bunch of machines, right? Once you have very kind of that single query for associated rule mania, the system knows how to automatically distribute that over hundreds of machines to deal with billions of tuples, right? So all of them are transparent for you as a user, but underneath the cover, there are decades of research about how to scale it up, right? Once you know how to do that in the database system, you do not need to optimize it all by yourself. You can just take advantage what people already know. So another tool functionality you can do inside a modern database system that goes beyond relational query is machine learning, right? So you can do clustering, you can do classification, right? So that's actually what my group is doing every single day on the research side. So I could talk about it for the whole semester, but let's not do that. So let's try to quickly introduce what are those operations in a very, very kind of shallow way, okay? We are not going to talk about the machine learning theory side. We are going to talk about essentially what they are doing. You think you understand the input and output, right, of those operations. And also we are going to show you how to do those inside a database system to make sure you know how to use them as a user instead of understanding them. Like, I mean, just not try to replace your machine learning course, right? You still need to try to understand, right? So what's underneath the cover they are really trying to do, right? Which is not something we are going to talk about in this course, right? But we want to make sure you know that, so that you can do all those operations inside the database system, right? So that's the goal. So clustering, this is actually a very interesting operation, right? So in general, I have a whole bunch of objects, right? So in my database, right? So I could have a whole bunch of students, I have a whole bunch of people, I have a whole bunch of transactions, right? So sometimes you could want to group them together such that objects in a certain group that we call a cluster are similar to one another, right? Or they are different from objects to another group, right? So that is the type of operation that we hope to do. So for example, if you have all of those objects, right? So every single dot is one object, right? So I could want to cluster them together to have different groups, such that if I take, and there are different notions about what do you mean by clustering them, what do you mean by similar, what is a good clustering strategy, right? But sometimes I could say, yeah, maybe all those objects within a group, they should be similar, right? Or maybe all those objects in different groups, they should be different. There are different notions of what is a good clustering strategy. But by doing clustering, essentially we are try to group all those objects into group all those objects into different clusters. And each cluster, the type is a subset of objects. So the notion of a cluster can be pretty ambiguous in the sense that if you give me kind of a data set, right? So if you look at it as a human, maybe it's easier for you to say, those subspace must be one cluster, this subspace should be another cluster. But when you really try to define them in a precise way, they are actually pretty hard to do. For example, if you look at this example, right, how many clusters should I have? It's actually not that clear right, what the answer should be, right? So you could put them into two clusters, right? One on the left-hand side, another on the right-hand side, right? You could have those kind of more fundamental ground notion of clusters. Right? You could have 6 clusters, right? And if you give that to a human, I mean, all of this strategy, I mean, at least makes sense to me, right? You could have 4 different clusters, or you can say, maybe like all these dots, they look like same population, and so on and so forth. So the notion of clusters can be pretty ambiguous, and people have been defining different notions for that. So, but intuitively, right? So what are we trying to do? So on the left-hand side, you have your database. So here we have a whole bunch of, I don't even know what it is, right? So, yeah, so this is actually some text information of a person, right? So you have person ID, right? So this is a tax refund, right? So the marital status of the person, the income, right? So every single row in this relation corresponding to essentially one dot in the space. And then what we are trying to do is try to group all of those rows in the database table, right, into multiple clusters, right? So if you want to think of that in a kind of mechanically, right? So essentially, we want to introduce another column, which is a cluster ID, and I want to assign every single row to a cluster ID. You know, that is essentially what we want to do. So a clustering strategy, right? So it's a set of clusters, right? So there are actually different notions of that. So there's two different types of clustering strategy that you could have. One is what people call hierarchical clustering. Another is partitional clustering. So the difference is that when you are doing one of those partitioning clustering, you actually have a partition of your data set. You are thinking about all those clusters. Each one of them is a partition of your data. If you take the disjoint of multiple clusters, you will get an empty set, which also means that every single data object belongs to exactly one cluster, okay? But you could have those hierarchical clustering strategies. That is, you have a set of nested clusters organized as a tree, right? So like both of them, people call them clustering, right? But if you think about the underlying semantic, it is actually very, very different. So this is one example of partitioning clustering, right? So your original data might look like this. One strategy is you put all of this into one partition, all of this into another partition, you introduce three clusters, right? So the property is if you take any of the two clusters and you take the intersection, you will get an empty set, right? So every single object only belongs to a single cluster. This is another example for hierarchical clustering, right? So assuming you have 4 different objects, right? So one way to cluster maybe say, P2 and P3 is one cluster, and then I put this cluster together with P4, I have another one. I mean, it's very similar to a family tree, right? So put the most similar thing together, you cluster them, right? So one example of this, if you want to, I used to do a little bit about biodiversity, right? So you have a whole bunch of animals, a whole bunch of plants, right? You have the family, you have order, you have all those things, right? So if you think about this, that is essentially one hierarchical clustering strategy. That is, for example, you have a whole bunch of different type of dogs. They all belong to one cluster called dog. You have a whole bunch of different type of cats. All of them belongs to a cluster of cats, right? So, and you put dog and cat together, they are one cluster of animal, right? So, and you can do that so on and so forth. So this is another way of dealing with the hierarchical clustering. That is, you have a nested hierarchical structure. Every single cluster is not a partition of your data because they overlap, but here you enforce a hierarchical structure. So people call both of this, the partitional way and the hierarchical way, people often call both of them clustering, right? So when you talk to other people, maybe you need to get this clear about what you really mean, because people might think about different things when you say, I want to cluster my data, right? So, and there are different type of clusters, like even if you talk about partitional clustering, right? So, I mean, that's actually a little bit tricky. And that's something I really want to make sure we appreciate, that is how dedicated it is to define a good cluster. So some of the clusters are kind of well partitioned, right? For example, here I have 3 clusters, and clearly there should be 3 clusters because they are so well partitioned, right? So, but you have a whole bunch of different ways you can define what is a good cluster. For example, there's a whole bunch of ways that actually is based on the notion of center. Okay, so essentially here, every single cluster is defined by the centroid, right? So you can see here you have one cluster, here you have another cluster. Right? What's the reason we don't put these two as a single cluster? Because here's my centroid, right? So here's also my centroid, right? So here essentially this is a center-based view for to kind of reason about like what is a good clustering strategy, right? So here we have for essentially center-based clusters, right? You can see there are pros and cons, right? The good thing about this is it's actually very simple, right? To define a cluster, right? I have centroid, right? So I have the radius, I'm done, right? So the bad thing is every single cluster look like a ball, right? Maybe that's good, maybe that's bad, right? But that's the pros and cons of this way of thinking about this. And you can actually define a clustering strategy to say, okay, I really think the continuous, if your object kind of covers a continuous space, I think there should be like one cluster, right? So one way to define it is for every single data point, you say, I look at my nearest neighbor. If within epsilon radius, I can find the nearest neighbor, then this two belongs to a single cluster, right? You can also think about a cluster in this way. You can introduce this kind of continuous notion of partitioning the space, right? So in this example, for example, if you take this example, right? You can see you are going to have two clusters here. And all of these examples, right? This kind of semi-ring, right? And it's going to be kind of like one cluster because it's kind of continuous, right? For every single data point in this region, you can find the nearest neighbor, right? And then for all of this kind of weird shape, right? So if you take the continuous view, all of this thing will become essentially a single cluster because there's a small bridge between them, right? I mean, you can see this, and there are pros and cons. For some applications, maybe you think, doesn't make sense. It should be continuous. For some application, you might think, it really should be center-based, right? So which one is good actually depends on your application. So like this is actually another example. Assuming you have data look like this, you have a whole bunch of data points here, whole bunch of data points here. If you take a center-based view, as we saw in the previous slides, you are going to have two clusters here, right? That makes sense. You have one center around here, you have another one center around the right-hand side. But if you take the continuous view, what you are going to have is a single cluster because there's one connected region, right, to connect these two. Which one is good? We don't know, right? You take one application and you think about what is the thing that makes sense for your application. I will try a whole bunch of those and try to see which result actually makes sense, right? But here, one thing that we really want you to know is when you are thinking about the clustering, it's very hard to have a universally good way to cluster your data. And that is really depends on your application itself. So you could have a different notion of clustering. You can have those density-based kind of clustering strategies. For example, you can define a cluster as a dense region of points, which is separated by low density regions, right, from other region of high density, right? So for example, in this example, like think about this. So this could be one high density region. This is another one. This is another one, right? So for different notions of clustering, you are going to have different results, okay? And sometimes you can actually define some shared property of objects, right? So for example, hypothetically that you say, so like I mean, like you can say all the points in the red region, they share some property, right? So then you are going to have this type of kind of like clustering results, right? So, but the point is that defining a good clustering strategy is a function of your application. So here we talk about a very simple way to cluster data. And if you are doing data science in practice, if you want to cluster data, sometimes this is the first thing that people would try. And that is k-means clustering, right? So it's a partitional clustering approach. That is for every single object, I assign that to one and only one cluster. Essentially, I want to partition all the objects in my database. And each cluster is associated with a centroid, right? So it's a center point of that cluster. And each point in the space, that is each row in your database, is assigned to a cluster with the closest centroid. Okay, so that is what the k-means is trying to do. So, and you need to tell the system the number of clusters, k, as a hyperparameter. So the object, if you think about what it's trying to do, is try to minimize the sum of distances of the point as their corresponding centroid. Okay, so essentially you want to assign kind of one example. So like here precisely, right? So assuming you have x point, so like you have a set of x, you have n points there, and every single point is an n-dimensional vector, right? So, and then essentially you want to assign for every single X is corresponding kind of cluster, assuming you have K clusters, you want to see K, right? So essentially what K-means is trying to do is I want to find the clustering strategy such that if I take a point X and its corresponding centroid, the sum of this distance is minimized, right? So over all the data examples, right? So essentially I want to minimize the total distance between every single point in my database and their corresponding centroid, right? So this sounds like a very simple thing to do. However, it is actually NP hard. If the dimensionality of your data, it's at least 2. Finding the best solution in this case in polynomial time is infeasible under very mild assumptions. So, and if you're dealing with a low dimensional space, for example, your dimension equals to 1, right? So every single point is a 1 point in that 1 dimension, right? Can be characterized as a single number. So in that case, it's actually solvable in polynomial time. But in general, when you're doing k-means clustering, it is often the case you have more than 2 dimensions of your data, right? In that case, it's actually NP hard to solve it. So, but there exists a very simple iterative algorithm that work actually quite well in practice. And it's very simple. You just assume that you say, okay, at the very beginning, I pick K points in the space as my initial centroids for my K cluster. And then you repeat the following step. That is, you assign all the data example to that K centroid, right? And then you form K clusters. And then you recompute the centroid of each cluster, and you repeat it until you converge. So it's a very simple iterative algorithm to do that. So, and when people say k-means algorithm, sometimes people just mean run this algorithm, okay? So it's very simple, right? So here's one example. Assuming you have a data example look like this, at iteration number 1, I could just pick, for example, 3 centroid, right? So randomly pick 3 centroid, and then I assign all the data example to its corresponding centroid. Then I have 3 clusters, right? And then you can see for each cluster, I can actually update their centroid. For example, after I do the assignment, all the green points corresponding to this centroid, and then if I recompute the centroid of the green cluster is going to move actually to somewhere like here, right? So you first put like randomly pick K centroid, you put all data example to that centroid, and then you recompute your centroid, right? You keep doing this again, and again. At some point, you are going to converge. And when you converge, you return, right? So if you run this process, as you can see, you are going to have 3 different clusters, right? So this thing is 1 cluster, this is another cluster, another cluster. Right? Yeah, so we have 1 question, go ahead.
Yeah, could you maybe re-explain the first step? Like, I don't get how you get to the different points assigning iteration 1, like, or you see how that works.
Oh yeah, so essentially you randomly pick 3 centroid. Okay, for example, you randomly pick this 3 point. And then for each data example, you find the centroid that's closest to it. For example, for this point, right, you calculate the distance between this point and this point, this, you say, so this centroid is actually closest to me. So I put it in the cluster associated with this centroid. Make sense? That's how you do the color thing.
Okay, and then how do we get, like, how do we compute the new point of the centroid?
Oh, yeah. So, and then you will have, for example, all of these brown points associated with this centroid. And then you just compute a new centroid as maybe the average, the median, whatever you want to do, right? So associated with all the brown points.
Oh, okay.
Like if you want to do the average, I mean, for example, if you take the green one, right? So if you say, it's actually my centroid defined as the average of all the points, right? So you can see in the second iteration, this centroid is going to move to the left corner, right? Okay. So I mean, that's why in the second iteration, the centroid is going to be here.
Okay, thanks. Makes sense.
Makes sense? Okay, yeah. So keep doing this. And you can prove under very mild technical condition, it's always going to converge, right? yeah, so at the end of the day, right, so you get 3 centroid and you assign your point. So one thing that's interesting here is your initial choice of all those centroid is going to have an impact on your final result. For example, if you take the same data set and you pick the initial centroid in a different way, for example, you put your initial centroid here, here, and here, instead of here, 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 right? So if you take a different position, if you run this algorithm, you probably will end up with a different clustering strategy, right? So essentially the algorithm that we define is kind of sensitive to the initial choice of all those centroids. So how can we deal with that, right? So what people often do is they do multiple runs and you pick the clustering strategy with the smallest error or loss, right? Defined as the average distance between every single point to their corresponding cluster, right? So select the original set of points, right? So you can actually have a whole bunch of heuristics other than doing that purely randomly, right? So, and that is actually something that you need to be careful when you're really doing k-means like in practice, right? So, and also another question that is, how can you calculate the centroid, right? So centroid depends on a whole bunch of things. So essentially, what is a centroid is like for a whole bunch of points, you want to aggregate them into a single point, right? And there are so many different ways you can do it. It depends on the distance function, right? It also depends on how to aggregate them, like all those points into a single point, right? You need to define kind of what do you mean by 2 points are kind of far away, like in which space they are far away, right? Should you have the Euclidean distance? Should you have a cosine similarity? Should you have different notion of similarity between points, right? You need to first define what do you mean by distance, and then you need to define whether the centroid is a mean of all those points, right? Or whether it is a median, right, under some other distances, right? So anyway, right, so you can actually define, like once you know the distance function, once you know like the aggregation strategy, right, so you know how to compute the centroid, right? So in practice, one thing that people often do is to assume the distance is in the Euclidean space, right? And then the centroid could be the average of all the points that's associated to that cluster, right? So, but that's only one way for to do it. And finding the centroid is not always easy because that's a function of the distance and also your aggregation function. So in practice, there are some instances of the problem that is actually NP hard to actually just find the centroid, okay? And for those type of problems, people actually spend years and years to develop different algorithms to approximate it. So it's actually not trivial, like how to find the centroid. You need to define the distance function, you need to define the aggregation strategy, then you have a well-defined notion of centroid. But even under that, it might be very hard to compute, right? So you do a whole bunch of approximation. But as you, as a user of the database system, you don't need to care about that. Okay, you specify your distance function, specify your aggregation strategy, specify how many clusters you want, and then the system deal with everything else, right? So that is our goal. So under mild condition, k-means will always converge. And most of the convergence in practice, right? So they actually happen in a very few iterations. So, and often like the stopping criteria of the algorithm is that you count how many points that change cluster across different iterations. If that number is small enough, then you're happy. Okay. So complexity, right? So if you think N is number of data points, K is number of clusters, I is number of iterations, D is a dimensionality, right? If you are doing Euclidean space, if your aggregation strategy calculate the mean to find the centroid, you have this complexity, right? For different type of distance function, you may have different complexity, right? You may have different dependency on the dimensionality. So in general, if you are not too crazy about the distance function you are using, it is a very fast and efficient algorithm. And that is why often when you are doing data science applications, if you want to cluster your data, this might be the first thing that you want to try, right? And there are a whole bunch of other ways you can do clustering, but k-means is popularly used because in many cases, it's very fast and efficient. Yeah. So k-means has problems. It's not universally applicable to all the applications, right? So it might not be a good strategy to do when you expect your cluster to have different sizes, to have different densities, or they are not a ball. Okay, so they have different weird shape. So in those examples, k-means may have problems. And also it might also have problems when your data have outliers, right? Because you are calculating the mean like between all the points, right? And your outlier could have a huge effect there. So this is just one example, right? So assuming I have like all of these kind of data examples, right? If you do k-means registry cluster, right, highly likely it's going to give you something look like this, right? So why? Because it's actually forced every single data example to be a ball, and it has a tendency to have a cluster of very similar sizes. Okay, so that is why it doesn't often give you the most intuitive result if your data example naturally fall into a cluster that's not of a shape of ball, or you have whole bunch of data example, like whole bunch of cluster with very different size. So that is one example that k-means could fail. Okay, so this is actually another example, right? So if you do k-means cluster, maybe, right? So if give you something like this, don't be surprised, right? So, and also if you have like a data example look like this, if you run k-means algorithm in the Euclidean space, right? So highly likely going to give you something look like this, going to put all of this into one cluster, all of this into one cluster, right? But as a human, if you look at this, I mean, naturally, I hope for some application, you might want to put all of this red dot together, all of this blue dot together, right? But if you run k-means, it's always want to have a ball shape, like in the space, right? So in this case, highly likely going to put all of this into one cluster and all of this into another cluster. So essentially, it's always trial and error, right? When you have one application, you have some expectation about what the cluster should look like, right? And then you run k-means, and then you need to check whether it actually makes sense or not. So like how to deal with it. So one trick that people play is you actually make k a little bit larger. You actually compute a whole bunch of clusters, and then you merge them in ad hoc way after you look at them, right? So for example, like in this case, if you say, so let's have maybe 10 clusters, you highly likely you are going to put all of this into different clusters, and then you as a human can actually look at it and then try to like understand the limitation of k-means clustering strategy, and you can merge some of them in whichever way that makes sense for your application. So inside database system, right? So that's actually very easy to do. So again, if you do Matplotlib, right? So you can actually do this in PostgreSQL. So essentially, you can actually create a table here. They call k-means sample, km sample, store all those data examples, right? So here is actually not in first normal form, right? You can actually store this kind of one list of numbers, right? One of them corresponding to essentially one like one feature, right? So like for your example, here you have 10 different examples, essentially 10 different points in the space. It's a really high dimensional space, right? So you can have a table look at this, and if you want to run, for example, k-means algorithm over this to cluster them together, right? So in Matplotlib, it's just this very simple query, right? So this is actually select from query, but goes beyond relational query because here you have essentially user-defined function, and you say, I'm going to run k-means clustering, right, over this relation. So this is the column that containing all of those coordinates, right? So here is essentially the second column, right? So that's all the vectors. And you say, this is the number of centroid, this is k equals to 2. I want to calculate 2 clusters, right? You define the distance function, you define the aggregation function. Combining these two will enable you to calculate the distance and also define what you mean by finding the centroid, okay? And then you can say, I want to run k-means for 20 iterations, right? So this is my convergence criteria. If you do this, right, so the system will generate a table that look like this. You will have essentially one like one cell here contains essentially the 2 centroid, right? So this is the first centroid, and this is the second centroid, right? So corresponding to the 2 clusters, right? And then after that, essentially you can actually do inference in the sense that you can actually take as input this data set and take as input these two centroids, right? And try to assign the cluster ID for each of them, right? So it's a very simple query look like this, right? So this is kind of your input table, right? The output table, all of this. Well, once you do this, you say, okay, originally I have 10 example, 1 to 10. This is the centroid that you assign to each of these examples. The first example is cluster 1, for example, the first one, cluster 0, so on and so forth. Okay, so it's very simple. If you want to do that inside your database system, prepare data in this way, and just one query away from getting the result of k-means. And of course, there are so many different ways that you can do to actually cluster things together, right? If you look at this, all those unsupervised learning, like a method, if you do the topic modeling, just give you a different way to actually cluster data together, right? Yeah, so whenever you need it in practice, just look it up. Yeah, and that is something you are able to do inside database. That is the most important thing I want you to know about after this lecture. Okay, so we have another. Hello, is there any question? Yeah, go ahead.
Yeah, sorry. So one question in the chat is, can MATLAB do kernels? I'm not sure what that means though.
I believe so. I believe it could do kernel k-means, but I'm not sure. Yeah. So I mean, there's so there's no fundamental reason why it cannot, right? But I'm not sure whether if you take MATLAB today, it can do kernel k-means. Yeah, but you can look at the reference to see whether it's supported or not. Yeah. Okay. Okay. So another functionality that we're going to talk about is classification, right? So what do we mean by this? This is actually different from clustering, right? So here, essentially, for every single row in the database, I have something I want to predict, right? For example, here's a very weird example. For every single person, you want to see whether that person cheated for tax return or not, right? So I have a whole bunch of training example in the history. I know all of these people, they actually cheated or not. And then if you give me a new guy, right, a new person, I want to actually predict whether that person going to cheat or not, right? So here, right, so essentially, like what you are like structure of the problem is you want to learn a target function f that maps the attribute set x to one of the predefined class label y, right? So here you have attribute set, for example, refund, mental status, taxable income. They could be of different types. They could be categorical example. They could be kind of continuous, right, as a value, right? But you want to have a function that take as input all of these attributes and output a single class. So here, the class is that either belongs to no or belong to yes. Okay, so that is essentially the the thing that we want to do. So it has a huge amount of applications, and if you look at the application of machine learning today in practice, many of those, a dominating amount of those, but not all of those, but a large amount of those actually falls into a classification problem, right? You want to predict whether tumor is benign, like it's good or bad, right? You want to classify kind of the credit card transactions, right? So as whether it's a fraud or not, right? You want to categorize news, like news story as finance, weather, so on and so forth, right? So all of this, right? So actually falls into a classification problem. So essentially, when you talk about classification, it's often have essentially two steps, right? So you have a whole bunch of training examples that you know the correct label, or you know some noisy order on the correct label. And then you try to build a classification model out of it. And then in the inference step, right, you have another kind of data set and another relation have the same schema, okay, as your training set, but you do not have the information on the class label, right? So here you want to apply your classification model to do inference to produce your best belief on the right class. So as you can see for classification problem, right? So by nature, we always have essentially two relations, right? So we have one relation serving as a training set, another relation serving as a test set, okay? How to evaluate it, right? So here if you are talking about a binary classification problem, right? So you could have this type of confusion matrices, right? So you have your predicted class from your machine learning model, and you have your actual class, and you can calculate the accuracy, right? And there are actually different ways for you to do it, right? So there's different metrics for you to evaluate kind of a classification model, right? And one thing that's interesting, right? So there are different ways you can actually build a classifier, right? So like machine learning community have been working on that for decades and decades, right? So one very interesting method there is called instance-based learning, right? And the one classifier there is called k-nearest neighbor classifier. That's very simple. That is like you give me one unseen case in the test set, right? You try to find the most similar example in the training set and just take its label, right? So the high intuition is that, okay, if I have this, I don't know whether this is this, right? So I just compare it with every single training example that I know about, and then I actually pick the one that's most similar to me and take its label, right? So this is a very, very powerful classifier. It might sound very trivial, but you will find it's actually very useful, given a whole bunch of other tricks. So yeah, if you think about how to define the type of classifier, you need three things, right? You need your training set, that is a set of stored record. You need a distance metric to compute the distance between different records, right? And then you want to have another constant here, we call it k. That is, I take the k nearest neighbor and then I aggregate their label as my prediction. Okay, so to classify an unknown record, you compute the distance of your unknown record to all the other training records. You identify the k nearest neighbor, and then you use a class label of nearest neighbor to determine the class label and of this unknown record. You can take majority vote, or you can take essentially like whatever aggregation function that you want to do. So how to compute the distance between 2 points? Yeah, there's so many different ways, right? So you can do Euclidean distance, you can do a whole bunch of other type of kernels, right? You can do whatever you want. In practice, there are a lot of tricks into play, but that's not what we care about in this course. So, and also you can actually take different number of nearest neighbors, right, for them to aggregate. So there's a whole bunch of theory about what is the optimal k that you can pick, right? But often in practice, that is a constant that's not too small, right? So you think about what the nearest neighbor is trying to do, right? So it's actually try to partition the whole space. For example, if your data point fall into this 2-dimensional space, into a whole bunch of grid look like this. That is, if you have an unseen example falls into this region, then it's going to take the label of this data example. Okay, so it's like so it's going to have this non-linear partition of this space. So, but this is really far away from definition of k-nearest neighbor. But now you understand its input and its output, right? So for classification problem, you have a training set, you train a model, right? And then you apply that to another relation, have the same schema, that's your test set. So you can do that in MATLAB in a pretty easy way. So for example, you can have your training example stored in this relation, right? So here you have the ID of this example, you have all the data, right? So here is a 2-dimensional space, right? You have 2 dimensions, and then you have your label. Here your label is integer, but it could be other things, right? So, and then you can see here I have 5 examples, have label 1, I have another 4 examples of label 0, right? So this is your essentially your training set for classification. And then you can actually create another relation for test examples, right? So the other example have the same schema as training example, simply you don't have, but you don't have the label, right? And if you want to train, I don't even know whether they train or not. Oh yeah, so and for k-nearest neighbor, right? So essentially you do not train a model, right? So for every single test example, you can just do the lookup, right? So you can just call this function and then you can get your inference result, right? So what do you need to give to this function? You need to give the relation name of the training set. You tell the system, okay, here's where you find the training set, right? So you need to tell, like this is the name of the column in the training relation contains the training features. This is your ID, this is where you find the label. this is your test example, right? So again, this is where you find the feature, where you find the ID. And I want you to output your inference result in this new relation, right? So here's a number of nearest neighbors, right? So, and here's the distance function, right? How to compare two different records. So once you do this, the system is going to generate a new relation storing the result, right? And then if you see what's inside this result, it's actually for this test example, I equals 1. This is a test example. This is the prediction from the system, okay? And of course, it's going to have other type of informations, right? For example, this is actually ID of the nearest neighbor. It's fine. This is the distance, right? So on and so forth. So this is just one simple example about how to do those classification model inside the database. So as you can see from the user's perspective, it's actually very easy to do. You give me the training set, you give me the test set, right? And then I give you the result. And you can do a whole bunch of other models. For example, in MATLAB, there's a whole bunch of like neural networks you can do, right? So all of this, I just really want you to understand at some point when you deal with a real world database systems, there are going to be a whole bunch of like regulation that maybe it's not often possible for you to move data from your database to another system like TensorFlow and PyTorch. When that happens, right? So just remember some type of machine learning you are actually able to do inside your database. Okay, just make sure you don't get confused when you really need it. Okay, so that's actually the purpose of this lecture. So this is all we have for today. Again, so the thing we are going to talk about in this lecture will not be in the exam, but that's something I really want you to know. So starting from next lecture, we are going to talk about something really interesting. That is, we talk about how to use database as a user, right? How to write a SQL query, how to design a schema. But we have never talked about how the database actually answer your query, right? All your information are stored on your hard drive, right? You give a query, what would happen underneath the cover? Starting from next lecture, we are going to open up that black box of database system, and we are going to see essentially layer by layer how a database system make it happen and what are the system optimizations the system is going to automatically do that for you. And we're going to talk about transactions, going to talk about recovery, going to like talk about like how to do data login, right? To make sure even if you pull the plug of your machine, when you reopen, your database is still in a consistent state. We are going to switch gear to talk about system starting this Friday. Okay, so that's all we have for today. I will be here to answer whatever question you have. Otherwise, I'll see you guys on Friday. Yeah, thank you. Okay, if there's no other questions, yeah, see you on Friday. Thank you.